Welcome one and welcome all to the Quimper Geological Society presentation. It's so great to have you all here today. My name is Rebecca Koronowski and I am the Engagement and Education Manager at Jefferson Land Trust. And I am here to support you all in having a great event tonight. So just a couple of things off the top about our platform here of Zoom. Hopefully you all are familiar with this platform, and if not, that is okay, welcome. We will be keeping most of our participants on mute for the duration of the event, and this is so that we can be sure that we're able to hear our presenters speaking without any distractions. However, if you would like to turn your camera on to show up and have your face visible as a part of the audience, in the lower left-hand corner of your screen, just to the right of the mute and unmute button, there's a start and stop video button there. And so if you're on camera and you'd like to turn your camera off, you can do so using that button. And same goes if you're off camera and you'd like to turn it on so that you can be a part of the live audience here for Michael and Will. Additionally, we will be using the chat feature here to send comments and questions into Michael and Will. So some of you already named that tune. Yes, that song was Penny Lane by the Beatles, and that was the Vitamin String Quartet playing that song there. And so that chat box will be where we will collect any questions for Will. And if you're having any technical trouble, you can get to me by chatting in that chat box there as well. And we will be having a Q&A at the end of the session where Michael will be posing some questions to Will. So as things come up for you throughout the presentation, feel free to pop those in to the chat box there so that we can compile some great questions for the end of our event. And with that, I will pass the mic on over to Michael Machette. Take it away, Michael.
Thank you. Thank you, Rebecca. Welcome to the Quimper Geological Society's Geology Lecture. It's being broadcast from our international headquarters here in Port Townsend, right out of Rebecca's house. A few things I want to mention. We'll have a winter news note going out around Christmas, just some things to keep you aware of what's going on. Secondly, our next speaker is a frequent member and presenter here at the Quimper Geological Society, and that's Scott Burns, a geologist and wine enthusiast from Portland, Oregon. That's going to be on June 9th at 4 p.m. And this is one which is going to go all over, going to talk about the terroir of wines in Washington, and we'll have a virtual tasting then too. So bring your favorite bottle and we'll work our way through it during the lecture. With that, let me just say a few things about Will. You read his bio in the notice, but I just want to mention a few things. That Will Gallin's the lead project lead on the carbon sequestration project at the DNR in Washington, in Olympia. He graduated in 2005 with a bachelor's from Carleton College, and then went on to get his master's at the University of Utah in 2010. He also has a second job at the DNR as a landslide mapper. So he's a man that carries two different kind of tool bags. His favorite geologic disciplines are sedimentology, stratigraphy, paleontology, and interestingly, salt tectonics, of which I think we have none in Washington. I got a smile at him, so I think that's right. On his off time, he likes to hike, read, and play with his two young children. So without further ado, we'll have Will Gallin speaking on the geologic carbon sequestration in Washington State. Will, it's all yours.
All right, thanks, Michael and Rebecca, and thanks for inviting me to. Thanks to the Quimper Geological Society. I'm going to share my screen now. Michael, can you see it?
We got it.
Great.
Hey, Will, while you're getting that set up, I'm wondering if we could pop some questions in for the audience to learn a little bit more about them.
Go ahead.
Okay, so we're passing a poll out to you all now. You can either tap if you're on a device or click if you're on a computer, and then click submit. We want to know where you're from and what is your geologic background. And this will help us to frame the topic and also just to learn a little bit more about who we're reaching tonight. So go ahead and either click or tap and then click submit to share those results with us. And I'll give you about 10 more seconds to get those in, and then we'll pause and I will share that information with all of you. Always good to know who we're talking with. So we're at about 80% of people answering. If you don't see a poll popping up for you and you are able to access the chat, you can go ahead and type the answers in, where you're from and what your geologic background is, into the chat there. Okay, I'm going to click end and share the answers with you. So not surprising, Port Townsend, the Quimper Geological Society headquarters, wins there with 38%. Also a lot of Washingtonians outside of Jefferson County. No international participants this time around, so we'll keep it to the continental US. And interestingly, a lot of you are here without a geologic background, which is awesome. Thank you for wanting to expand your horizons and learn a little bit with us. Oh, and someone is saying they're married to a geologist. Well, that's an honorary geology degree if I've ever heard of one. Okay, I'll stop sharing and I will pass it back over to you, Will. Thank you.
Okay, great. And Rebecca, can you see my screen again?
I can. Looks
Okay,
great.
Okay, hi everybody. I'm Will Gallin at the Washington Geological Survey, which is part of the Washington State Department of Natural Resources. I'm presenting geologic carbon sequestration in Washington State today, and this project is funded in part by the Department of Energy. The partnership that they're funding is the Carbon Utilization and Storage Partnership for the Western United States, which is an interagency award that we share with New Mexico Tech. There we go. So the objective for tonight is to describe the current state of geologic carbon sequestration in Washington State. So this is not a survey of all the solutions to climate change, and this is not a lesson on what climate change is. Just in order to focus my talk. That's what the objective is. The agenda is first, I'll give a brief explanation of the problem that we're dealing with, anthropogenic climate change. And then I'll describe the one solution that we're talking about today, which is one of many solutions to this problem. I'll describe the method of how we sequester carbon geologically. And going through that, I'll describe where the emission sources are in Washington State, how we capture and compress the CO2 gas, how we transport and inject it, and what exactly is the process of geological sequestration. And finally, how do we monitor the injection process? I'll go through the risks in this process and what mitigation tools we have. And I'll cover the economics before describing a couple of current events in this topic and concluding. So we have another survey question here, and Rebecca will bring that up in a second. So the question is, what are your thoughts on anthropogenic climate change? Do you think it's a hoax? Do you think it's real but not a big deal? Is it a problem that must be solved? And these kinds of questions they're just to keep the audience engaged, but it's also interesting for me as somebody presenting to the public how I can change my presentation or change what I have to teach people about as I go forward presenting to the public.
Okay, Will, and here are the results for you.
Thanks. So that's 96% say it's a problem that must be solved, and a couple of people think it's real, but it's not a big deal, not that much to worry about. So we're going to move ahead now, and just a little review on how greenhouse gases affect our atmosphere. So we've got the sun up top, and we've got the Earth down there, and the sun emits solar radiation. And some of that solar radiation reflects off of usually bright surfaces on Earth, whether it's in the atmosphere or ice caps. But some of that solar radiation is absorbed. And that absorbed solar radiation, usually on darker surfaces like water or dark vegetated areas, gets re-emitted as infrared radiation. Now, if we lived on another planet that didn't have an atmosphere, that infrared radiation, which is just heat, would just go back out into space. But we've got an atmosphere with gases, and 78% of that atmosphere is nitrogen, and 21% is oxygen. The other 1% is mostly argon, but then a couple of other gases, which include greenhouse gases like CO2 and methane. So what happens when infrared radiation hits nitrogen or oxygen, which is most of the atmosphere? It just passes right through those molecules. But when infrared radiation hits CO2 or methane, which are more complex molecules, it makes them vibrate. And the way that they vibrate, they re-emit infrared radiation, so heat. And some of that re-emitted radiation goes out to space, and some of it heats up the atmosphere, and some of it is sent back down to Earth's surface, and that heats up Earth's surface. So even though these are a tiny fraction of the atmosphere, they have an important role in heating our planet. So this might be a little bit bright on your screens, but it is a graph of the CO2 concentration in the atmosphere from the last 800,000 years. And we have that from ice cores drilled at the poles. And the x-axis on the bottom is time, with 800,000 years in the past on the left-hand side, and going up to the present day at 0 on the right-hand side. And the y-axis is carbon dioxide concentration in parts per million. So it's low concentration on the bottom of the y-axis and high on the top. And as you can see, it goes up and down as different factors affect our Earth over time. But as you can see in the top right-hand corner, our current concentration is about 2 times higher than pre-industrial levels. And that's significant because it's modeled that at 2 times higher the pre-industrial levels, the average surface temperature of the Earth will increase by between 2 and 8 degrees Fahrenheit. And that has implications for melting ice caps, raising sea levels, mass extinctions. This is a major and very fast change in our planet's temperature. So one solution to that problem is to try and find areas where we emit carbon dioxide and other greenhouse gases, which are the red dots on this example map, and try to find locations where we can store those gases underground, which are the blue dots. This map is a map of the Southeast US that was modeled by the Los Alamos National Lab. And this is what we are going to do in the Northwest and the Western states as part of CUSP. We're joining with the national labs to try and figure out the best way, the most optimal paths to link those red dots, those emission sources, to reservoirs where we can store CO2. And the green are the pathways, our pipeline pathways, optimal pipeline pathways. So as I mentioned, Los Alamos National Lab is a major player with us in the Carbon Utilization and Storage Partnership for the Western US, which the acronym is CUSP. So that is the project that we've started. It's funded by the Department of Energy, a $5 million grant about $300,000 is budgeted for the Washington project, of which 20% is provided by the state of Washington. And it's a 3-year project with the chance to extend. And the award was announced in September of last year, but we didn't get a contract signed from the feds until February of 2020. So that also might lead to the project being extended a little bit. And as well, there might be some sort of COVID extension because the project began right as COVID started. So it's an interagency agreement, as I mentioned at the beginning, with the principal investigator at New Mexico Tech, that's Dr. Bob Balch. And there's also a co-PI, Brian McPherson, at the Energy and Geoscience Institute at the University of Utah. The partnership includes 18 state geological surveys, national labs, and universities. And the national labs include Pacific Northwest National Lab in Richland, out in Eastern Washington, as well as I mentioned, Los Alamos and Sandia National Labs. And in all, that's 13 states that are partnered up here. There are 3 other partnerships for other parts of the United States. So what is our work as geologists in this partnership? This is the most recent carbon storage assessment for Washington State from before our partnership. And the blue is the median CO2 storage capacity in million metric tons. So the darker blue means more storage and the lighter blue means less storage. And potential storage. And as you can see, they only cover the western part of Washington State. So that is something that we need to fix. And the reason why they only covered the western part of Washington State is that that's where sandstone is. The green dots on this map are oil and gas wells, and oil and gas wells are usually drilled into a conventional reservoir like sandstone. And you can use those wells to pump CO2 back down into the ground. So in the time since this assessment was made, we've figured out that we can also pump CO2 into basalt. And the Eastern Washington State has a lot of basalt, 210 square kilometers of basalt. It's a huge, it's a large igneous province. It's a huge area of basalt. And there are other issues we need to fix on this map. The grid is a pretty low resolution grid. It's a 10 kilometer by 10 kilometer square. That's what those little grid cells are. And we need a, if we want to actually start these projects, we need to get a more refined grid, so higher level of detail. And then there are also, problems that a Washingtonian might pick out on this map that maybe a national survey did not see. Is that, for instance, if you can see my mouse, Mount Rainier over here and Mount St. Helens over here, that's considered on this map a high capacity area. And that's not true. There's no way we're going to be able to store CO2 or want to drill into storage CO2 under those volcanoes. So that's not happening. We've got a couple things to fix, and that is going to be what my role is. So I just on that previous slide, I gave the units as million metric tons. So let's talk a little bit about weight and the weight of this gas. And if Rebecca wants to put the next survey up, that would be great. So when I drive my car, let's see, my screen is covered up a little bit. When I drive my car, my exhaust emissions either weigh less than the gasoline I burned, weigh the same as the gasoline I burned, weigh more than the gasoline I burned, or you don't have to worry about it. You don't drive a gasoline powered car, and the electricity that's powering that car is not hooked up to a coal-fired power plant or natural gas power plant. And then this was I'll just let you know as I'm watching your responses come in. We can see your responses as they come in, but I want you to know that this is the answer to this is, a surprise to me. I'm not a chemist by background, and I just never thought about it this way. So Rebecca, whenever you want to show the people what their votes are.
Yeah, people are taking a little bit longer on this one. It seems like it's a bit of a harder question. So yeah, just make your best guess. I did not know the answer to this either until Will told me earlier when we were practicing. So just a couple more seconds. And here we go.
Great, thanks. So most people said that the car exhaust, the gases that are emitted are going to weigh less than the gasoline that you burned, that you pumped into your tank. And the strange thing is that they actually weigh more. So that was the second highest gas at 33%. And the reason for that is that if you think about it, the gas that you burn in your car is chemically bonding with oxygen in the atmosphere. And an oxygen atom actually weighs more than a carbon atom. The atomic weight of an oxygen atom is 18, the atomic weight of, or 16, sorry, and the atomic weight of a carbon atom is 12. So you get 2 oxygen atoms joining with every carbon atom from the gasoline. You're going to be a lot heavier than the gasoline that was actually burned. And then the rest of the stuff in your gasoline is just carbon and it's hydrogen. So the carbon is joining with the oxygen and the hydrogen is joining with water, joining to become water. So that's a strange thing to think about. And then also, as we go forward, the reason I wanted to put this survey in was to tell you that we're going to be using weight, so metric tons. If you see MT in this presentation, that stands for metric tons. And if you see MMT, that stands for million metric tons. So we're measuring the CO2 instead of in volume, we're measuring it in mass. So I'm going to move ahead now. Okay, so what is Washington going to do about the problem that we're dealing with? On this bar chart, the orange is 2017, and those are real emissions. The Y scale is million metric tons of CO2 emitted every year. So the orange is what we're around where we're at right now in 2020. We don't have data for 2020 yet. The blue bars are what the state energy strategy seeks to reduce emissions by each of these years. So in 2020, the state of Washington wants to be down to 1990 level emissions. In 10 years from now, they want to decrease our emission levels by 45% from the 1990 level. In 2040, they want to decrease it by 70%. And in 2050, they want to decrease our emissions in Washington state by 95% below 1990 levels. And all of these reduction targets are meant to keep global temperatures within 1.5 degrees Celsius of pre-industrial levels. That's the goal here. These are not just arbitrary reduction levels. And why 1990 as our goalpost? That's the first year, and you'll see that in a lot of climate work. 1990 will come up a lot, and that's because that's the first year that the International Panel on Climate Change ran their global emissions inventory. So in 2050, we want to be down 95% below 1990 levels, but you may have heard that the state wants to actually be carbon neutral by 2050. So what happens with that remaining 5%? The remaining 5%, according to the state energy strategy, which is a state statute, this is in our law, the remaining 5% is meant to be offset by either biologic or geologic sequestration. So is that something that's going to be possible to sequester 5% of our 1990 levels of emissions with biologic and geologic sequestration? Well, I think it's possible with geologic sequestration alone. But biologic sequestration will help a lot, but we're not covering that in this talk. This is a view of some Columbia River basalts. And we can store, we've found this goal is achievable. We know that we can store in this basalt because in 2013, we drilled a basalt test well at Wallula in Eastern Washington. And in just 3 weeks, that well injected about 1,000 metric tons of CO2. And in the years of monitoring after that well was drilled, we found that not only was it injected as a supercritical fluid, which is almost like a liquid-like fluid, but that gas, which had been turned into a supercritical fluid, had solidified within 2 years. About 60% of that gas had solidified into a limestone-like mineral. So the special thing about the basalt is that not only is it a reservoir for the gas, but it also permanently stores that gas as a solid. So it becomes an inert solid, which is not going to get back up into the atmosphere. So now I'm going to go through the methods. of geologic carbon sequestration. So we're going to start off talking about our emission sources in Washington state. Then we will talk about capture, which is the separation and the compression process for that gas. Then we'll talk about transport, how we pipe that gas. Then we'll talk about the CO2 injection and how the CO2 is actually permanently trapped in that rock. And finally, we're going to talk about how injection is monitored during and after injection. So first, we're going to do the CO2 emissions. And before I show you the maps of where those emissions are in Washington state, I want to clarify some terms. I'm going to show you the point sources in Washington state. And point sources, which is represented on the left, which is a Chehalis coal-fired power plant with Mount Rainier in the background. Point sources are what you can think of as smokestacks. They're factories and power plants. It's much easier to capture carbon when you have a stationary emission source. About 45% of Washington's emissions are tailpipe emissions. So that's coming out of the exhaust of your car. And it's much harder to capture CO2 emissions from a moving target like a car. So the next couple of maps are going to be the 55% of Washington's emissions that come from point sources. So there's a significant number of people that we saw in the survey at the beginning that are not from Washington state. So I made these maps assuming that most people were from Washington, most people at this talk. So please excuse me that there's no place names on here. I'll just move my mouse around. This is Puget Sound over here. This is the Olympic Peninsula. This is the Quimper Peninsula where Port Townsend is. Seattle is on the Sound. I live in Olympia down at the south part of the Sound. And then the eastern part where the Columbia River basalts are, that's over here in eastern Washington. And the Cascade Mountains are a ridge that go like this. I'm sorry if you can't see my mouse, and I will put some name labels on these in the future. But I also like the simplicity of these maps. In each of these maps, I'm going to have bubbles, colored bubbles. The smaller the bubble, the smaller the amount of CO2 emitted per year. And the larger the bubble, the larger the amount of CO2 emitted per year. And the color of the bubbles are going to be the industrial sector that's represented. So this is the other category. All of these data that I've plotted are from EPA data. Industries that emit above a certain level have to report their emissions to the EPA, and that's public information. So the other category includes agribusiness, it includes the universities, it includes the military, it includes Boeing and tech and other manufacturers. And a lot of these dots are actually landfills, they're waste facilities. So they're all small emitters in Washington state. And moving next to the next category of emissions in Washington are pulp mill emissions. So these are paper and pulp mills that produce enough to have to report to the EPA. And there's actually this one over here in eastern Washington in the southeast part of this slide. That's the Wallula Gap. That's a cardboard box manufacturing facility, Packaging Corporation of America, which helped us with running the Wallula test well. So we'll talk about that more later. Metals and minerals in Washington state. There's a large aluminum industry in Washington state, which dates back to the World War II and Depression era building of dams in Washington. So there's a aluminum smelter up in Whatcom County. There's aluminum manufacturing in Wenatchee and Spokane. And then the rest of these dots are cement manufacturing in Seattle and glass manufacturing in Chehalis and Moses Lake. So the next slide, the next map I'm going to show you is going to be a map of where our refining is in Washington. And here's another survey question before we get to that slide, because this was something that was surprising to me before I moved to Washington. Among the 50 states in the US, Washington ranks which highest in petroleum refining? Are we the 5th highest refiner? Are we the 37th highest refiner? Or are we the 49th highest refiner? And let's see what people think. And it looks like as I can watch, as I said, the answers come in live. It looks like a lot of people have the right answer. I was surprised by this, and most of the people that I've talked to in Washington don't know this, so don't be shy to guess. And whenever you're ready, Rebecca, to show the answers.
We're at about 70%. So make your final guesses and we'll end the poll.
It's
And here we
people
go.
can see now 65% of you guessed correctly or knew, and knew the answer already. It wasn't a guess. We are the 5th highest refiner in the US. The only states that have that refine more petroleum products than us are Texas, Louisiana, California, and Illinois. And that's the last 2 years of data. So where are those refineries? Washington State has 2 refineries up in Whatcom County, which are at the BP facility at Cherry Point and the Phillips 66 facility in Ferndale. In Skagit County, there are 2 other large refiners and these are up in the north part of the state, those big purple dots up in the north. There's a Marathon refinery at Anacortes and a Shell refinery at Anacortes. And then down in the Tacoma area, which is over here, there's a smaller refinery which mostly produces jet fuel for JBLM, the military base down here. The rest of the purple dots on here are chemical manufacturing from petrochemicals, except for on the east side of the state, there's a string of these large, medium-sized bubbles, and those are compression stations for a pipeline that comes down from Canada through Washington and Oregon to California. So as the crude is piped down, there need to be pumping stations along that route. That's what those dots are on the east side. So this is a larger emitter than the previous categories. And then the largest emitter of all of our industry categories that we're covering are our power plants. Washington has a lot of hydropower, but we also have natural gas power plants. So all of these are natural gas power plants, except for one large yellow dot in Chehalis, which is a coal-fired power plant, which is slated to close in 2025. And then there's also on the Oregon side, right across the border from Wallula, there's a coal-fired power plant in Boardman, Oregon, which is slated to close in about 10, 15 days, however far we are from the New Year's. So those are being shut down. The rest of these, as I mentioned, are natural gas facilities. And then these, I've put all the bubbles together. These are all the EPA reported emissions in our state. And then, and again, these bubbles this is 2018 data from the EPA. So this shows where everything is. And there is, as you can tell, there's along the I-5 corridor, along the western part of the state, that's where the major emissions are coming from, which is not surprising. But there are significant emissions over on the east side of the state, including emissions from Oregon and Idaho that could be brought over to be stored in our basalts on the east side. So moving along, we just described the CO2 emission sources, and now going ahead, we're going to describe the capture process of separating and compressing the gas. So I'm going to show a couple of facilities pictures, and this might be boring to some people, but I find it easier to understand what exactly is going on the ground if somebody shows me a picture rather than just saying the word capture or compression. I want to know what that actually looks like. So the capture sites for point sources are actually going to be, they're actually facilities built at the power plant or at the factory. And these are absorption towers from a capture facility in Japan. And what happens is the flue gas, which is the smoke that comes out of the smokestack from a power plant or an industrial facility, is piped into these towers, and then it's chemically mixed to pull the CO2 out. So it's a chemical process in these towers. And then I also want to show an example, even though it doesn't have to do with the point sources that we are dealing with. I did want to mention direct air capture. So direct air capture is a technology that's seeking to capture the emissions from all those tailpipe emissions from the ambient atmosphere. And here's an example from near Zurich in Switzerland of a direct air capture facility. So there might be questions in later about how economic the direct air capture will be, but we can talk about that later. So once we've separated the CO2, to capture the CO2 and then separated it chemically from the other gases coming out of smokestacks, we want to compress it. And that's in order to be able to pump it through pipes. It needs to be squeezed and pushed along those pipelines. So on the left-hand side is an image of what one of these compressors looks like in operation. And on the right-hand side, we have an example of conveniently showing what it looks like as a cutaway. And these compressors they look like jet engines. They're a series of fans that as the gas is sucked into the fan and blown along, it is squeezed by these very powerful fans. So those were examples of the capture process separating and compressing the gas. So now we're going to talk about CO2 transport and CO2 injection. So when we talk about CO2 transport, we're talking mostly about pipelines. That's the cheapest way to move a fluid. There is also rail lines, and there's also tankers, but that's much more expensive. So on the left-hand side is a pipeline, CO2, specifically a CO2 pipeline from near Casper, Wyoming. Wyoming is moving forward pretty quickly with carbon sequestration projects. And on the right-hand side is what it looks like at the injection site. This is the actual injection site for the Wallula, Washington injection project. And so there's a wellhead here. It's like a mini Christmas tree, this black thing down here. That's what the wellhead looks like. All this other stuff will be removed after the injection process. And then there's some compressor in the back over here to help inject the CO2 down the well bore. That was a quick look at what transportation of the gas and injection looks like. But now the meat of what I want to talk about, this is where my expertise is, and this is in how we actually get the CO2 trapped within the rock. So the easiest way to think about injecting CO2 is to think of it as the inverse of exploring for oil. And when you're exploring for oil or gas, the elements that you need are, you need a trap, which is a shape of a rock that can trap that buoyant oil or gas. And then you need an impermeable seal. That means a rock that fluid cannot flow through. And I'm moving from top to bottom on this slide. Then you need a reservoir that's both permeable and porous. That means pores, that's the space that the fluid can be kept inside of, and permeable means that the fluid can flow through it. And then when you're searching for oil or gas, you also need a source rock, like a rock with a high organic content. You also need heat that can turn that source rock into oil or gas. When we are sequestering carbon, we don't need the source rock, and now, of course, we don't need the heat that turns the source rock into oil or gas. I kept gas up here because CO2 is a gas. What we're going to be doing is we're going to be pumping the CO2 into a trap, a bowl or other trap-shaped rock. And then we're also going to be pumping it into a rock that has permeability and porosity, a reservoir rock. So in order to figure out where those good locations for carbon sequestration are, we can use our oil wells as a proxy, because we're going to be doing the inverse. We're going to be pumping down the oil wells instead of pumping up out of the oil wells. So this is a map of where oil wells are in Washington state. Most of these wells, there are about 800 of these wells, and most of these wells were drilled between 1900 and the 1960s. There are a scattered number of wells between the 60s, 70s, up to 2012. But most of these wells are early on. And what we can do is we can look at the basins based on where these wells are. And so I'm going to run through now where our basins are, where we have reservoirs that we can pump CO2 into. There's the Olympic Peninsula. That's actually a basin. There's Oil City on the west side of the peninsula, but this is a bad location for pumping CO2 down. So don't freak out yet as I have this on the screen, because it's both remote from emission sources. It's mostly taken up by the national park, and there are significant tribal lands in the area. But also geologically, it's not a good location. There's a lot of complexity to the geology, and it is definitely not low-hanging fruit in terms of carbon sequestration. just slightly better, there's the Willapa Hills area. There's, you can see all the wells that were drilled there. There is reservoir there, but there's minimal pipeline infrastructure, and it's not near any, it's pretty far from major CO2 emission sources. And slightly better, one of our two focus basins is the Puget Basin. And the reason why that's a basin of focus is that it has significant sandstone reservoirs going from Bellingham all the way up through this, down through the Seattle area to Chehalis. And many people don't know that the Chehalis area also has one of the United States' largest gas storage facilities at Jackson Prairie that's run by PSE, our natural gas provider for heating our homes. So they actually get gas from refiners, and then they pump it down into the sandstone in the Chehalis area, and they store it there until you need it to heat your stove, and then it's pumped out of that storage facility and to your house. The significance of that is that that already proves that gas can be stored in those traps in the Chehalis area. So that's good to know if we also want to trap carbon dioxide and similar traps. The Puget lowlands are, they have major emission sources. There's the existing pipeline infrastructure along the I-5 corridor. And, but on the other hand, it has the heaviest urban development. So it's going to be really hard to try and begin a project anywhere in that area. You're going to come up against a lot of resistance in terms of land use. However, on the east side, we do have significant sources of CO2, maybe not as high intensity as the Puget lowlands, but they are significant. And then we also have basalt, which, as I mentioned earlier, as opposed to sandstone, that basalt will not only trap the CO2, but it will mineralize it permanently into a limestone-like mineral called anchorite. So we are focusing first on the Columbia Basin. And finally, there's the Cascades area, the spine going up and down Washington. That's not prospective. There aren't reservoirs in that area. And then there are the Okanagan highlands in the northeast. And all those wells that you see in the northeast part of this slide, those were follies. Those were not, those were all unsuccessful wells. There isn't good reservoir rock in that area. So earlier I mentioned that we need a reservoir that has permeability and porosity. So this is a picture of Columbia River flood basalts from the east side of the state near Palouse Falls. And what I want to show you on this slide is that the cliffs of, these are from flood basalts from Miocene, so from about 15 million years ago. And when these basalts were pouring out of the ground, they would pour out and flow, and then the tops of the flow would get vesicles. So all the gas bubbles would flow to the top of those lava flows, and it would make the top of those lava flows, when they cooled and hardened and solidified, into a good reservoir. The tops of those flows are both they're both broken up so that there's permeability, and they also have all these bubbles in them, so that makes the porosity. So in this picture, each of these cliffs, generally the cliffs areas here are going to be the basalt flow bodies, the impermeable colonnades and the columns of basalt that you're used to seeing in Washington. But then at the tops of these flows, the ledges are generally going to be that broken up, more permeable and porous reservoir unit. So this is an image of what we're thinking of and what Wallula Gap has already been pumped into. So this slide, it's just one slide in this presentation, but this is what most of my work is going to be. On the left-hand side, we have a core drilled from the Wallula Gap well. And you can see it's got that Swiss cheese consistency. Those are the bubbles from the salt, from the gas in the basalt flowing to the top and then getting trapped as the basalt hardened and solidified. So that's our reservoir. But how do we find that when we can't just look underground? One of the best tools that geologists have at their disposals for subsurface geology is well logs. And every time an oil or gas well and some water wells are drilled, they lower a big tool down the hole, and that is what the center image is. It's about, could be 40 foot long tool. And that tool collects all kinds of geologic data. And on the right-hand side is an example from the Wallula Gap of a well log from that well. It's a density log. This is a log that shows what the density of the rock is. And the lower density areas in this rock are going to be the areas where there's going to be a higher porosity and permeability. So we're looking to, I'm going to be mapping what those low density zones are, and that will help us find our sequestration prospects. So where has this been done? In 2012, the CarbFix project outside of Reykjavik in Iceland injected 175 metric tons of CO2 into basalt. And they found that basalt also solidified quickly into a inert mineral, a carbonate mineral. This is what they drilled. They have an example of their porous basalt on the left-hand side. That's just an example of basalt. And on the right-hand side, they've drilled a core after their injection, and it shows all the white minerals filling all the pore spaces. And those white minerals are CO2 that's been taken from the atmosphere and injected into the well, and then has mineralized by joining free ions of iron and magnesium that are in basalt, and joining that with the CO2 to form carbonate minerals like siderite and anchorite, which are similar to limestone and calcite and dolomite. Where else has basalt been tested for CO2? The other location in the world is the Lululu Gap well in Washington. And we injected about an order of magnitude more, about 1,000 metric tons of CO2 in 2013. And we had similarly successful results. And this is this aerial photo shows the Columbia River in the foreground with the cardboard packaging plant in the middle, and the Wallula Well is right there by the plant. So the idea is to have locations where we don't have to transport the CO2 that far. We can try to get it as close as possible to the emission sources. This is an example of a core from the bottom of the Wallula Well showing the carbonate nodules that have formed and from the CO2 that solidified after we pumped it in. Where else is CO2 injected in the world? So those are I just told you two examples of CO2 injection from into basalt, but CO2 has actually been injected into more conventional reservoirs like sandstone and limestone for many years now, but it's been done by the oil industry and not by, I guess, what they call pure play geologic injection. The Equinor, which until recently was Statoil, the state oil company of Norway, they have been injecting, on average, 1 million metric tons of CO2 annually since 1996. And they were triggered to do that by laws in Norway restricting emissions. So they've been injecting that into sandstones beneath the North Sea. The other largest, very large CO2 injection is at the Sackrock field in West Texas, and that's a series of oil companies that are co-operators, and in injecting 400 million metric tons of CO2 since 1972. So they've been doing this a long time, and there are plenty of studies on what this does to their facilities, what this does to their well bores, how the CO2 flows through the reservoirs. There is a history of CO2 injection. It's not actually a new technology. It's just that it hasn't been much in the public eye. So these two last examples I've given, the Sleipner example and the Sackrock example, those are both something called EOR, which is enhanced oil recovery. These companies use CO2 to try and push more oil out of the rock. They end up having a net negative emissions because more CO2 is going down into the rock than is being pulled out by oil and gas. But if you're interested in stopping any kind of fossil fuel emissions at all, you might be more interested in basalt injection. So we've talked about the CO2 emission sources, capture, transportation, injection, and the sequestration. So now I'm just going to briefly talk about monitoring during injection and after injection. So here's a photo from the Wallula Well at the wellhead of a sampling process. And the way that we can monitor these wells to verify that the CO2 is going down and make sure that it's not leaking out is through fluid sampling, core sampling, seismic monitoring. There's surface gas detection, and there's well pressure testing. So there are many ways to try and make sure that this CO2 is staying in the hole. So before we get to the next slide, I want to wake everybody up in case you've fallen asleep. You know, it's very quiet on my end. And I want to see if people have an idea of how many vertically stacked space needles below the ground is the depth of a carbon sequestration well. And this is a little bit tricky because what I'm saying is what is the minimum depth for one of these? So they can go, you know, we can drill as deep as the economics will allow us, but in terms of keeping the CO2 in a supercritical state, which is a liquid-like state, so we need the right temperature and pressure levels in order to keep it at that level. How deep does it have to be? Because pressure increases as you go farther down. About 60% of people have voted. And just to give you an idea, the Space Needle is 600 feet high. I think we're slowing down in responses, so now if you want to share that with everybody, Rebecca, that would be great. Thank you. So as everybody, we guessed correctly. So 5, we want to get optimally between about 2,500 and 3,000 feet below the surface in order to keep that CO2 under pressure in the reservoir. And I'll show you a little graphic we made about what that looks like. So here's a little graphic. Oops, there's something didn't work right on the animation. You can ignore the words on the bottom for now, but the animation on the left shows our space needles stacked on top of each other. And this, as I mentioned, is a minimum depth. We can go quite a lot deeper than that. You know, so in this, on the Columbia Basin, most of our groundwater wells, just for reference, are going to be between tens and hundreds of feet deep. So there's a little groundwater aquifer up at the top. We are drilling very far away from those aquifers down, quite a bit down into the basalt, where all the formation water is much higher than 10,000 total dissolved solids. So much saltier, where you can't use the water for drinking in the first place. So this slide, I'm also going to discuss on this slide the risks involved. So what are our potentially undesirable outcomes, and what are the existing mitigation tools that we have? And most of these mitigation tools come to us from our national labs. So there's induced seismicity. Anytime you're pumping something into a well at pressure, there's the problem of possibly triggering earthquakes. So the national labs have something called the short-term seismic forecasting tools. And this is something where you can see earthquakes don't just come out of nowhere. They start with very, very minute shaking that can't be sensed by people at all. But you can sense that with geophones, with our tools. And this tool shows that, you know, once you start sensing those, you can ease up on the pressure in order not to trigger an actual earthquake. There's also the potential for damage from seismicity. National labs have made a modeling tool in order to figure out where are higher risk areas to drill. There's a potential for accidental hydraulic fracture. I want to lay all these things out in front of you. There's a small possibility, but there is the possibility of that. And so there's something called the state of stress analysis tool. And similar to the induced seismicity tool, this tool models what the stress is on the well. And as you increase your pressure, how are you getting closer to the envelope of triggering hydraulic fracture? And so you can ease away from that pressure before hitting that. There's the potential for unintended formation communication. So there's something called the Designs for Risk Evaluation and Management tool by the national labs, which helps model how formations might communicate. Formations are these rock layers on the left-hand side. So you don't want CO2 flowing from that bottom rock layer to any of the other rock layers. And we can also drill groundwater monitoring wells, and shut down a project if it shows that it's creating a plume that's spreading, and possibly contain that plume by pumping water into those monitoring wells. Then there's the problem of possible well underperformance. What if we pump CO2 down into the well, but it gets all clogged up? And we have reservoir engineering modeling, and we've got well pressure testing to help us with this potential risk. And then finally at the bottom, which was on the screen the whole time, there's the potential for CO2 surface leakage. And we can monitor that at the surface with gas detectors and know if there's a problem if we see higher levels of CO2 at the surface. So there are all risks. These are all risks, but there is potential for mitigating these risks. There are other risks that are not geologic. Anytime you build any kind of industrial facility, you may be putting the public's environmental health at risk, or you might be worsening social vulnerabilities. So Washington State, the Washington State Department of Health, along with the University of Washington and a series of not-for-profit agencies, have an excellent tool online, and the website's there on the bottom, where they map environmental health disparities and social vulnerabilities by census tract. And so the red on this map are higher risk areas for environmental health disparities, and the blue are lower risk areas. So as any industry wants to plan this, we want to take this into account as a risk as well, and we want to mitigate that risk. So economics, I'm going to go through the whole method process here and just give you a qualitative view. The most expensive part of the process is the capture process, because you don't just have to build the capital project for the facilities, the absorption facilities, but you also have an ongoing operational cost that's much higher than the operational cost of a well or a pipeline. A little bit less expensive are the pipelines, and less expensive also is the injection well. A compression facility might cost in the order of tens of millions of dollars, but CO2 transport, that's on the order of tens of thousands of dollars per pipeline diameter per mile. So the bigger the pipeline and the longer the pipeline, the more expensive. And the wells can cost between millions and low tens of millions of dollars. Monitoring is going to be the cheapest part, but that said, the EPA is underfunded. So somebody's going to have to come up with some of that money where the EPA can't. So I mentioned capture cost. This is a graph showing different capture facilities on the bottom with a bar, but I haven't put any of the units yet because there's ongoing economic research into how expensive each of these are. But just to give you a generalization, this is the order of tens to about $100 per metric ton of CO2 captured. So if you want to capture 1 million metric tons, you want that dollar per ton value to be low. So on the low end, we've got natural gas processing, ethanol. It's easy to capture and separate CO2 from the gases from those processes than it is on the right-hand side of the slide to remove CO2 from food processing facilities or oil and gas extraction or distribution or metals manufacturing. So how do we bring these costs down? Here's a slide with an IRS form. In 2018, there was something called the Bipartisan Budget Act, which was passed, and that increased the incentives for carbon sequestration, something called 45Q. If you want to Google search it, search 45Q. That's the section of the US tax code. And it takes an act of Congress to change this. So, as administration changes, it's going to be hard to change this law. But what this law did in 2018 is that it increased the incentives for companies to store carbon in the ground. And it actually made the incentive for capture that's not EOR, capture like our basalt projects, that incentive was made much higher than EOR. So that's a good thing if you want CO2 to be captured permanently and not used to pull more fossil fuels out of the ground. There's also, in California, there's a carbon tax and a low carbon fuel standard, or LCFS. And there's a possibility for legislation popping up again in Washington for that this year. So keep your eyes out for legislation this year on that, whether to see whether Washington will pass a low carbon fuel standard. That legislation creates a market which might also make carbon sequestration more economic. Finally, there's the issue I mentioned in the last slide of EPA funding. There's a bill that was meant to be brought to the House floor this past week, but wasn't because of COVID legislation that is meant to increase EPA funding, and that would help with the permitting process. If the EPA can't permit wells and if states don't have primacy for permitting on their own, if they don't apply for that from the EPA, then that can slow down the process, and companies don't like slow processes. If it takes 7 years to permit a well, they're going to spend their money somewhere else. If the EPA gets more money, then companies get their tax incentives faster. So that is the economics of this. So now we're going to just do current events. This is Petronova. This is this was the largest carbon sequestration project in the world. It's outside of Houston, Texas, up until August. And in August, it closed down. What happened there? The Petronova closure in August, there are a couple of issues. One issue is this is at a coal-fired power plant. You can see the gondola cars filled with coal in the back of the picture. This linked this one coal-fired power plant to one reservoir, which was an EOR project trying to pump CO2 into that reservoir to get oil and gas out of that reservoir. So part of the problem is that it linked one emission source to one reservoir. And what we want to do is we want to have a more flexible system where more sources are interconnected with more reservoirs in our pipeline system. The other major problem here is that the COVID crash in oil prices. It was not economic for this project to run anymore as oil prices fell. But with our Basalt project, our economics should not be based on oil price. So that should keep us a little bit protected from that problem. This slide is a little bit light on my screen, but if you can see the bubbles on it, it's a map of the US, showing currently planned sequestration projects. There are about 38 currently planned sequestration projects. Only 2 of these are in their final financing. The rest are in something called FEED, the front-end engineering and design stage of starting a project. But they are colored by the source of CO2. So the dark blue are industrial emission sources, and the light blue are power plant emission sources. There's only one direct air capture, and that's source, and that's that magenta dot in West Texas. So that's the only place in the US where they're planning on capturing CO2 from the atmosphere. That's the only project that's actually currently in planning stage. Most of these projects from North Dakota and Illinois down to Texas are EOR projects. They are collecting CO2 from industrial sources and power plants, and they're planning to pump that into reservoirs in order to get more oil out of the ground. If we want to not have more oil pumped out of the ground, we could have a big dot in Washington that's over on the east side of the state in the basalt, not in an oil producing area. So in conclusion, I hope I didn't go too long. I didn't have my timer on. We covered the emission sources in Washington state. I'll give you a brief look at what capture and compression is like, and a brief look at pipelines, the transport of CO2, as well as what injection looks like and what the geology of sequestration is. And then I briefly talked about monitoring these sites. My job as we go ahead at Washington Geological Survey is to refine the maps of CO2 storage and identify prospects. So I put a little prospect map on the lower left-hand corner. And then I will give my prospect maps to CUSP, and CUSP has all these people working at the national labs, the modelers working at the national labs, the economists. They will identify the optimal point sources to connect CO2 emissions to reservoirs. And at that point, we will give the information to the public, and we are not running these projects ourselves. It's up then to industry themselves to determine whether they want to pursue storage in order to comply with statutes that are increasing across many states right now, carbon neutral emissions statutes. And finally, if any project does go forward, if industry chooses a project in Washington, the Washington Geological Survey will be there to provide geological assistance to ecology or EPA, whoever is doing the monitoring, reporting, and verifying compliance work. So that's something that might go beyond CUSP, that we might need state funding for on our own in order to provide that geological assistance. So I want to thank CUSP, which is the partnership I'm part of. I want to thank the Quimper Geological Society for inviting me. They are pros at this. Thank you for putting together all the surveys. That was great. And I want to thank Jordana Averitt and Maria Fertney, whom I work with and who helped me out at Washington Geological Survey. So if you want to email me any of your questions, I'm not going to be answering them right now. We're going to do that over the chat, but feel free to, my email's on the screen, and the DNR Geology website is there on the screen as well. So that's the conclusion. Thank you.
Thank you so much, Will. That was awesome. I see some folks clapping in the stands as well. It's hard to tell, but we're all here and we're all paying attention.
It's a very strange thing to present not in a lecture hall, but in a silent living room.
If you stop sharing your screen and take a look, you can see all the smiling faces of people.
Okay, hi everybody.
Saying thank you. Yeah, thanks for being here, folks. You all have a lot of really awesome questions. So Will, if you're up for it, Michael and I can read a few of those to you right now. And for anyone who needs to take off, we are just slightly past time, but if you'd like to stick around and hear some more Q&A and get a little more detail from Will, feel free. And just a reminder, we will have another one of these events next month. So if you are not on the Quimper Geology email list, please do sign up so that you get more information. And Michael's going to tell us a little bit more about that next event after our Q&A here. So Michael, what are some of the questions that you've been getting from the crowd?
Well, they started out slow, but then they're a crescendo about 5 minutes ago.
Mm-hmm.
I don't know if I can summarize these. Can you see these, Will, these questions in the chat room?
Yeah, I can.
So on the right, there's a time signature, and that's the best way to refer to them because they're not numbered in any sense. So I think one of the first ones I got that was fairly serious was from Paul Bellinger, who's a professional geologist, and he was remarking about a Wikipedia site about the conditions of liquid and oxygen and vaporous carbon dioxide. I see if I can find it right now.
Okay, so if that's in, and you can just interrupt me if I'm not getting to the point of the question, but something I did want to mention is that there were two different processes between the Iceland injection process and the Wallula Gap process. In Iceland, they mixed dissolved CO2 in water and injected it. And that mineralized very, very fast, but a lot faster than the Washington site did. In Washington, we compressed the CO2 into supercritical state, which is a liquid-like state. So the CO2 wasn't dissolved in water, but it was sent down on its own as a supercritical fluid. And that took about 2 years to mineralize 60% of the gas injected. So the question is, why wouldn't we just use the Iceland method? And the reason is that the Iceland method takes a lot of water, and we especially don't want to, water resources are something important in Washington. We don't want to necessarily cause some other problem by using a ton of water, especially on the east side, to inject CO2 into the formation. Other issues that I don't know whether these are the main issues, but when you have dissolved CO2 in water, there's a high acidity, and that can cause corrosion on your pipes. So I don't know whether that's a major issue for the CarbFix project in Iceland, but there are different methods even within the basalt injection. There are different methods of injecting.
At 4:33 p.m., Polly Lyle states the Kamala, a methanol refinery, if built, would emit 4.6 million metric tons per year. You have something to say about that?
I don't. Is that a Washington site, the methanol site that they're planning on building in Washington?
Polly's here or not?
Okay.
I don't know if it's been permitted or not.
Okay.
Anybody ring in on that? Okay. A little bit later, Jeff Tepper asks, does sequestration plans assume that existing wells will be reused? Are there any plans to sequester CO2 in ultramafic rocks such as the Twin Sisters dunite?
Yeah, so I'll start with the second one, the Twin Sisters dunite. If you haven't seen Jeff talk about igneous rocks or anybody else, there's a piece of mantle that's been exhumed, and that's what the Twin Sisters Massif is, near Mount Baker in Whatcom County. And that is an entire set of mountains that is almost pure dunite. And dunite is about 95 or 97% of olivine. So that's an even richer example of where you can bond CO2 with a mineral that will help mineralize that CO2. So the question is, why don't we drill wells up there? I think it's much harder to drill into that rock. I don't know if there will be as much, there might be more public resistance to drilling in the Twin Sisters Massif. But really, I think the issue is, and this is an area that climate scientists are interested in. You may have heard online people talking about grinding up olivine and seeding beaches with olivine to help deacidify the oceans. That seems a little bit out there and could cause more problems, but there is interesting research in possibly using ground up basalt for CO2 capture in crops, similar to somebody else here. I think Paul Bellinger was talking to me earlier this week about biochar. So it's possible to do that too with ground up olivine, but I'm not an agronomist. I don't know how exactly that would work. But there is a lot of interest in the Twin Sisters Massif. We're not looking at it as a drilling target. As for the first part of the question, what was the first part of the question again?
Cooling joints and other factors degrade the ability to steal CO2.
I'm sorry, I didn't hear that. But I can answer. I remember the first part of Jeff's question is, are we looking to
use existing wells?
Yes, use existing wells. And the answer is that is something that we would like to do instead of having to drill new wells, but there are always costs involved in recompleting a well. Sometimes it might be more expensive to recomplete a well than to drill a new well, especially if these wells are very old. We don't want to use any wells that are before a certain date when we can be sure of the quality of their cement jobs. So every time you drill a well, you want to seal off the formation so that you don't get pollution from one unit to the other. And you need to do that by cementing the area between the inner annulus, the steel pipe that you're putting down the hole, and the outer annulus, which is the rock. You want to make sure that cement job is done right. A lot of these very old wells are pretty crummy when it comes to cement jobs and casing. So if we are going to reuse any wells, it's going to have to be a much more recent well, and those are few and far between in Washington State.
Okay, we had a few questions about the texture of the basalt. For example, John Karachewski, who joined yesterday, our newest member, says, I would expect basalt vesicles to have high porosity, but relatively low permeability. And I made the same content. Yeah. Same question. Are these vesicles interconnected, and how does the communication go?
Yeah, so that's something that was surprising to me too. I think of it as, holding that core example. I think of this as being Swiss cheese, but the problem with Swiss cheese is that none of those holes in the cheese are connected to each other. But it turns out that At Wallula, they found that they had very high permeabilities. These are in the order of hundreds to low thousands of darcies, of millidarcies. So up to almost a darcy, but very high permeability. I was surprised by, and the reason for that is that it's not just that the vesicles are flowing to the top of the basalt flow, but as they cool, the tops of each of these basalt flows fracture. And then if there's any time before the next basalt flow where there's weathering, we have a stack of these basalt flows that have flowed out very fast, but they flowed out fast in geologic time. And in reality, there might be, 1,000 or 10,000 years between each of these basalt flows. And in a time period like that, you can have the top surface of the basalt flow weathered. And that weathering process also creates cracks in the rock that lead to a higher permeability.
Okay, we got lots of questions. I'll just go through a few more. John, Will's going to get all these chat remarks. And if we didn't answer your question in this little session, then you can send him an email if you've got a burning issue here. But Sharon says a couple of questions. Isn't CO2 a commercially viable product? What's the cost, both financial and energy-wise, for chemical and repressurization process?
Yeah, so I don't have the number off the top of my head for different industries for reusing that, but see, the reason why CUSP is called CUSP, the reason why it has the letter U in it is for utilization. We're not planning any kind of utilization project in Washington state, but utilization, the major source of utilization right now in the US is EOR, enhanced oil recovery, but there are other non-oil utilization methods. There's, you could have food products, there's CO2 in food, but that's going to need a lot of, that CO2 has to be very, very clean before it's, much cleaner than, 99 or 95 or 99%, which is what we do with separation. There are a series of other industries which are more notional. I mean, they're being developed right now, but they're not commercially viable like EOR is right now. So that is also a possibility. And the reason why we have utilization in our title is because we want that option also. We want to be able, if as these industries, start, we want to be able to connect them up to our network. And there's legislation that's also trying to be passed called CIFIA. It's Carbon Infrastructure Financing and something else Act. And it's similar to WIFIA, which is a water act that was passed in, I think, 1998 or 2014, and a TIFIA, which is a similar act passed for transportation. And these are all ways that people have tried to get the federal government to help kickstart some of these infrastructural changes.
Okay, let's see, we're running, it's about 5:15. How about one more question, then we wrap it up? And I'll say a few words about the next lecture, but I want to tell you now, Will, we really appreciate this. It's been a great lecture, something I didn't know anything about really. So
thanks, and sorry I went over.
Oh, no problem. Time's cheap for me. I'm retired. Jeff and another person asked basically the same question, is what happens with the CO2 if it prematurely plugs the vesicles and reduces the permeability? Do you ever get to the end point of maximum saturation?
Yeah, so I'm not a reservoir engineer, but I did work in the oil industry before coming to Washington. And there are ways to deal with CO2 blocking whatever your migration routes are. I don't really want to comment too much on that because the methods that we use in the oil industry, I don't know whether they would be appropriate for Washington. And what that would be is in Texas, what you would do is you'd acidize a well. You'd send acid down the well, which would remobilize some of that CO2. It would keep it in the rock, but it would keep it flowing. But there are all kinds of environmental issues that I'm not sure that would be appropriate in Washington state. I think that these wells need to be, we had very good results from the Wallula Gap well, but there's got to be a lot of planning involved before we actually inject it to make sure that those migration pathways are going to be kept open. We don't want to be working on the back end to fix a mess rather than to prevent one from the start.
Okay, and one remark for me is that would you say 40% of the sources are moving vehicle type sources, and hopefully the new advent of electric cars, both hybrid and full electric, will eliminate or reduce a lot of that emission for us. We can, you can't get at that point of it, but maybe the environmental.
I actually, yeah, I do want to just share one slide. If it's too late for that, just shut it down. But if you can see my screen, I put in a slide in my backup from Lawrence Livermore National Laboratory. And what this is this graph shows where Washingtonians get their energy from and where it goes. So the colored bars on the left are all where we get it from. We get a lot from hydro compared to other states. That's in the dark blue. But then we use it in electricity generation, residential, commercial, and industrial heating and processes, and transportation. But the dark blue, the dark gray box over here on the right-hand side, that's how much energy we actually use. And the much larger light gray box is how much energy is wasted, mostly through heat. And most of that waste of heat is either through heat from cars or heat from electricity, heat from idling cars, or heat from electricity transmission. So we don't have a efficient system to start with. And the state energy strategy actually focuses a lot. We only have 5%, which is going to be geologic sequestration, but a huge portion of our work going ahead is going to be trying to figure out how to change our transmission systems to be more efficient, to lose less of that electricity to heat, to use more of that electricity, run that electricity when we are actually using it and not have it lost. So this is about a 23, or I think, sorry, a 30% efficiency that we're running at right now.
Okay.
So.
Okay, back to me, Rebecca.
Yeah, go for it. Thanks for that clarification, Will. That's a really interesting graphic that you just shared.
Yeah, and that's public information. So if you want to go on to, if anybody wants to Google search Lawrence Livermore National Lab energy flow charts, you can find that for your own state. You can find that for the US as a whole.
Okay, Rebecca wanted me to mention the next lecture, which will be, I already mentioned it a little bit, but I'm gonna pimp it now. January 9th, Scott Burns, retired professor of geology from Portland State University. He's an expert at the relationship between geology and wines and vineyards and grapes. And he told me that he recently gave a Zoom lecture to 5,000 people that were interested in terroir, the relationship between geology, climate, soils, slope, water, all these things, and how they impact what the actual taste of the wine will be from grapes that are grown on it. So in this lecture, we're going to have a virtual tasting. So we want you to get your favorite bottle of wine out there with one or two or maybe more glasses. And as we go through Scott's lecture, we hopefully be tasting and thinking in our mind is, how did this wine turn out to be so darn good? Anyway, that'll be on our website. It's actually right there, a little preview for it. And that's coming out. That's going to be in just a little less than a month. So that's all I have, Rebecca.
That's great. Thank you, Michael. And I just dropped some links into the chat there. So if you are not on the Quimper Geological Society mailing list, you can go to quimpergeology.org and sign up to get announcements for all of the future events, like the one Mike was just telling us about. And if you have any questions for Will, again, we can share his information with you, and he put that on his slide there. I think there were a few more questions for you there. We thank you so much, Will, for being here with us tonight. Everyone in the chat has been super excited about the presentation, and I learned so much from you today. So thank you for being here. It was a wonderful presentation.
Thanks for having me.
To all of you, thanks for spending your night with us. Hopefully you're off to dinner or happy hour or something enjoyable for the rest of your evening, and we'll see you again here next month. Take care, all.
Bye.
Bye-bye.